Good afternoon, everyone. Myself, Punnam. I am working as an assistant professor in EEE department, Mlritm. Today, I am going to explain the mathematical modeling of a system. So, this presentation outline is mathematical representation of a control system or model, and types of a mathematical model, mathematical modeling of a electrical system, and transfer function of a electrical system. So mathematical model represents the mathematical representation helps in the analysis of a system. It captures the dynamics of a system. For example, the change in room temperature when an AC is switched on, the change in the speed of a car when an accelerator pushed by the certain angle, the change in current flowing through an inductor when an AC voltage is applied. So types of mathematical modeling: differential equation method, transfer function method, and state space model. So differential equation method is a time domain representation of a system. And this model describes the system using a differential equation. And the transfer function model, the frequency domain representation of a system. This model describes the system using Laplace transform expression. And finally, the state space model is a state space is a set of variables that describes the system behavior using the first order differential equation or a higher order differential equation. Now, types of mathematical modeling. Let us consider a RLC series circuit. I want to write the mathematical model for this RLC circuit. So first of all, I want to use some basic laws for a given circuit. So the basic laws are KVL and Ohm's law I am applying. So this is plus and this is minus, this is plus and this is minus, this is plus and this is minus as per the current direction I. So when current enters at positive terminal and it is leaving at minus terminal, so now I want to write a KVL for this equation, for KVL for this circuit. V applied voltage is equal to IR plus L into di by dt plus 1 by C integral I dt. 1 by C integral I dt. If I divide this equation by L on both sides, I will get that the differential equation so V by L is equal to R by L into I plus di by dt plus 1 by LC integral I dt. And substitute I is equal to dq by dt. Then you will get a second order equation d square q by dt square plus r by L into dq by dt plus 1 by LC into q is equal to V by L. So this is one of the differential model, second order differential equation. Okay, so if I consider the output voltage is VC here, then I will get a differential equation for this particular circuit is d square V of t by dt square plus R by L into dV of t by dt 1 by LC. V of t is equal to 1 by LC Vi of t, which is input. If I separate the V of t, v naught of t is common, and after that if I apply the Laplace transform of it, then s square d square v of t by dt square will gives you s square v naught of s plus r by l into s v naught of s plus 1 by lc into v naught of s, which is equal to 1 by lc into vi of s. So this is a frequency domain representation. After that, take v naught of s as common and rearrange it v naught of s by vi of s, which is output by input as a transfer function. You will get 1 by s square lc plus s into rc plus 1. So this kind of representation, is called as transfer function representation. So transfer function is defined as, it is the ratio of Laplace transform of input, Laplace transform of output by Laplace transform of input, with all initial conditions is set to be a 0. And third type of mathematical model is state space model. If I assign a state variable for particular differential equation, I will get that this kind of equation, which is in the form of x dot of t is equal to a into x of t plus b into u of t. So this is called as state equation. Here a is equal to minus r by l, 1 by l, 1 by c, 0, a matrix. This is a matrix and this is b matrix. The differential equation model is, as I said earlier, plus minus plus minus plus minus, and I am considering here output as v naught of s. So applying KVL, input v of t, vi of t is equal to r into I of t, voltage across resistor, plus L into di of dt, voltage across inductor, plus v naught, which is output, which is voltage across capacitor. Now the current passing through the capacitor is C I is equal to C into dV by dt. Substitute this I value here. Then I will get Vi of t RC into dV by dt plus 1 LC into d by dt of d by dt V naught of t plus V naught. So this is a second order differential equation. So V naught Vi of t is equal to RC dV naught by dt plus LC into d square V naught of t by dt square plus V naught of t. So complete equation becomes as a in the form of V naught of t and I naught of t. From that I can write the transfer function easily. Vi of t is equal to RC into d into V naught of t by dt plus LC d by dt of V naught of t by dt plus V naught of t. So this is a second order differential equation. After rearranging d square V naught of t by dt square plus r by l into d V naught of t by dt plus 1 by c LC V naught of t, which is equal to 1 by LC into V of t. So this kind of representation is called as differential equation of a second order differential equation. Now the similar differential equation can be converted into a transfer function or transfer function model by doing a mathematical tool, by using a mathematical tool which is Laplace transform method. So Laplace transform of d square V naught of t by dt square is s square V naught of t, V naught of s plus r by l into d V naught of t by dt is s into V naught of S plus 1 by LC V naught of is equal to plus V naught of S is equal to 1 by LC into V of S, Vi of S. So V naught of S by Vi of S is equal to 1 by LC by S square plus R by L into S plus 1 by L into C. So this is a transfer function representation. This is a transfer function representation of a RLC circuit. So the basic elements of a electrical systems are resistor, inductor and capacitor. So as we know that voltage and current relationship in a V, resistor is V is equal to IR, I is equal to V by R is equal to V by I. And inductor, in inductor it is an element stores the electricity in the form of magnetic field. So the voltage across inductor is V is equal to L into di by dt, and the energy stored by the inductor is 1 by 2 Li square. And the capacitor stores the energy in the form of electrostatic field, and the voltage across capacitor is equal to 1 by C integral I dt, and energy stored by the capacitor is equal to 1 by 2 CV square. So transfer function of a RC circuit is, consider a RC circuit and apply the basics laws for it. Now I am applying KVL in this loop and considering voltage across capacitor as a output. So V input, V in is equal to voltage across resistor plus voltage across capacitor is equal to the current through the resistor is I. Current through the resistor is I of t. So which is equal to R into I of t plus 1 by C integral I dt. Voltage across capacitor is 1 by C integral I dt. Applying Laplace transform for it, applying Laplace transform for so by KVL, Vi of t is equal to voltage across resistor plus voltage across capacitor, that is 1 by C integral I dt. Okay. So I is equal to apply Laplace transform for above equation 1. So Vi of S is equal to R into I of S plus 1 by Cs into I of S, since integration gives 1 by S. After taking LCM, RCS I of S plus 1 into I of S and take I of S as common is equal to 1 plus RCS by C of S, which is equal to output. I of S is output and V naught of S is input. Sorry, Vi of S is input. So Cs by 1 plus RCS. So this is a transfer function representation of a given circuit. Now transfer function of a RL circuit. by KVL, V of t is equal to VR, voltage across resistor, plus voltage across inductor. Voltage across inductor, and I am considering output as current I naught, I of t. So voltage across resistor is equal to I into R, and voltage across inductor is L into di by dt. I V of t is equal to IR plus L into di by dt. Now I am applying Laplace transform. So V of S is equal to R into I of S plus L into S I of S. I of S, I am taking it as common, R plus LS, which is equal to I of S by V of S is equal to 1 by R plus LS. So transfer function I of S by V of S is equal to 1 by, if I take it as L common, S plus R by L, 1 by L by S plus R by L. So this is a transfer function for a given RL circuit. Transfer function. Next, transfer function of RLC circuit, and I am considering in this output is current. So by KVL, V of t is equal to voltage across resistor VR plus VL plus VC. By Ohm's law, VR, voltage across resistor, is current into I into R, plus voltage across inductor is L into di by dt, plus voltage across capacitor is 1 by C integral I dt, which is equal to V of t. So this is my input, and I am considering in this circuit as current as output. So current I is equal to rate of change of charge dq by dt. Now I am substituting current value in above equation, R into dq by dt plus L into d by dt of dq by dt plus 1 by C integral, and differentiation gets cancelled, and q by C, q into 1 by C. Now L into d square q by dt square plus R into dq by dt plus q by C. V of t is equal to After taking Laplace transform, V of s is equal to L into s square q of s plus r into s into q of s plus 1 by. So finally, q of s by v of s is equal to 1 by L c by s square plus r by lc plus 1 by lc into s. So this is a transfer function. Differential equation. So v of s is equal to s square into I of s plus r by L plus q by c into I of s. L s square plus s plus 1 by c. Divide both sides by L. I of s is equal to s square plus r by ls plus 1 by lc. So output I of s by v of s is equal to 1 by L by s square plus r by ls plus 1 by lc. So this is a transfer function model.